Start? All right. Is it bouncing? La, la, la. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for the nice change in weather. And pray that you just bless this class today. Help us to all finish the semester well, Lord, just to capture each day, Lord, for your glory. We thank you, Lord, that if we accept you into our heart, we have your righteousness rather than our own. Because your righteousness is worth having, but ours is like filthy rags, and we accept that and acknowledge that. And I just pray that you just guide this class today, Lord. In your name I pray. Amen. All right. Well, I wanted to prove something. So, here goes. Theorem 12.8.2, and it states the following: if the sum over k of a sub k x to the power k converges at c not equal to 0, it converges absolutely for all x with the absolute value of x less than c. Furthermore, if the series ak x to the k diverges at d, then it diverges at all x with absolute value of x greater than d. Now, you might recognize this theorem. I proved it in a special context, in a slightly different language before. All right, I assumed that we had power series that had all non-zero coefficients, and I used the ratio test to give us this result essentially. But I noticed in Salas and Hilly, this is from Theorem 12.8.2 from page 91 of the PDF I posted, or their page. Come on, show yourself page number 617. That there was this nice, simple little proof, and I thought it was worth our 5 minutes. So let's do it. And so here's the proof. Suppose that ak x to the k converges at x equals to c not equal to 0, right? Then what can we say about a to the k, c to the k as k goes to infinity? What does this go to as k goes to infinity? Can you fill in the blank for me? Yeah. 0, right. This is the kth term test, right? So, therefore, for k sufficiently large, and by the way, I should point out, thus, the absolute value of a sub k c to the power k goes to 0, right? as k goes to infinity just the same. If we have a sequence goes to 0, then the absolute value of the sequence also goes to 0. But if the absolute value of this sequence, a sub k times, c to the power k, is convergent, what do we prove about convergent sequences? They're bounded. So in particular, for k sufficiently large, we may bound the absolute value of ak c to the power k above by, let's say, 1. Right? Certainly, if this goes to 0 as k goes to infinity, if we go far enough out, we can make them within 1 unit of 0, right? And what he says is this gives, thus, for such k, we have that the absolute value of a sub k, x to the power k, right, is equal to a sub k x over c times c to the power k. So I just divide and multiply by c, but then laws of, so that gives me a to the k, c to the k, absolute value, times the absolute value of x over c to the power k. Which is less than or equal to what? So using this right here, I can drop that in favor of 1, and that gives me x over c to the power k. Right? Therefore, if the absolute value of x is less than c, right? And if, if you write this, what can we say about c? C negative? No. So c is equal to the absolute value of c. That implies what? The absolute value of x over absolute value of c is less than 1. Or simply the absolute value of x over c is less than 1. So if we look at such x, I want to prove that the given power series a to the k, a sub k, x to the k converges absolutely for such x. How can I do it? With the inequality I have on the board and the observation that I have about these x. Let me make another statement here. How about the direct comparison test? Can we do direct comparison? We can do direct comparison of the given power series. Direct comparison test of, the sum, ak x to the k, right? In fact, not that, but the absolute value of that, right? Against what? The sum over x over c to the power k, right? So we know that the given absolute value series is smaller than the series x over c to the power k. But what is this x over c to the power k series? It's the tail of what? Blank series with r equal to absolute value of x over c less than 1. Fill in the blank. I heard someone whisper loudly geometric. Or that was in my head. Either way, I'll take it. Geometric, yeah. So we can, with this sneaky little couple line proof, form a direct comparison of the absolute value of the given series with the geometric series. And since the absolute value series converges, that means that this given power series converges absolutely on its open interval of convergence. So, you know, sum a k x to the k converges absolutely for, you know, minus c less, for x, an element of minus c to c, right? And while I haven't proved this for you guys, absolute convergence is important because absolute convergence forbids this pesky thing I mentioned before about conditionally convergent series. Conditionally convergent series, by Riemann's rearrangement lemma, can be rearranged to come out to any value you like. In contrast, an absolutely convergent series, you can reorder this, you can rearrange the order in which you're adding the terms, and it does not affect the outcome. If you think about it, this is very important for us as we've done series calculations, where we've been rearranging terms willy-nilly to do calculus. If those kind of rearrangements, if multiplying series out and it mattered which order you collected terms, right? If it mattered which order you collected terms when you're multiplying series, this would be very troubling because have I multiplied two power series out the same way 2 days in a row? Probably not. Like I distribute it a different way every time I do it, right? And that doesn't matter because they're absolutely convergent and rearranging terms doesn't change the outcome. If they were conditionally convergent, we'd be in trouble. Anyway, that's the proof of claim 1. And what would the proof of claim 2 be? He says, suppose now that you have a series that diverges, then there cannot exist an x greater than d at which it converges, because if it did, that would imply the absolute convergence of the divergent series. So I won't write that down. It's in the book. I'll let you read it. But this is the main thing I wanted to get across to you guys. This is an improvement of what I did. Why? Because the proof I gave you before assumed that the terms were what? The coefficients, the a sub k's were non-zero, right? But we can actually do better than that if you compare to the geometric series. So that's maybe that's kind of striking, right? Because we've used the geometric series to prove what in here at this point? What did we use geometric series for? If I recall correctly, ratio test, root test. Now, even really, the fundamental theorem about domain of power series rests on the geometric series. Right? Geometric series is really important to our thinking. Okay, well, I suppose. 0, 6, 5, 6. Sorry, my 5 minutes turned into 14 minutes. My apologies. I want to show you something else. It is unfortunate that at the moment we don't seem to have a course on special relativity here. Do you guys know what special relativity is? So special relativity is modification of Newtonian mechanics, which is needed when the velocity of light, when the velocity of a material particle gets close to the speed of light. So one of the things we learn in special relativity is that the energy of a mass m sub 0, m sub 0 being the rest mass, is equal to m0 c squared times gamma, where gamma is 1 over the square root of 1 minus v squared over c squared. So here, m0 is the so-called rest mass. V is the velocity. And c is the speed of light. All right, this is all taking place in a vacuum, more or less, or air is pretty good too. And I'm thinking about, I mean, you could think about one-dimensional motion if you like. You could let velocity, if it's not, it's velocity if it's one-dimensional, you could say, or speed if we're talking about, it could be the speed squared. V squared could be the, or V squared is V dot V. But that's kind of a next, let's just keep it one-dimensional because we don't have calculus 3 yet, so we don't know about, you know, whatever. So this gamma function is what? If we wanted to, so suppose that the velocity is much, much smaller than the speed of light, right? And I'll stick with, you know, the absolute value of the velocity is much, much smaller than the speed of light. All right. So what would that say? What would that say about the absolute value of V over C then? It's much, much less than 1, right? Or you could say that V squared over C squared is much, much less than 1, right? So V over C in this context would be a very small quantity, right? In this discussion. And if you look at gamma, it's actually equal to what? It's actually equal to 1 minus V squared over C squared to the what? To the minus 1/2 power, right? So how would we expand this as a series? See, the other application of series beyond just power series calculation that you should be aware of, in fact, this is probably the more important thing for applications, is the idea that a series allows us to approximate an expression with a polynomial. And this is usually done with respect to some guiding assumption. In this case, the guiding assumption is that the velocity is much, much smaller than the speed of light. If that's the case, then I know that the quantity V squared over C squared is a very tiny thing. So that means I can use the binomial series here, right? Because this is really 1 plus u to the minus 1/2 power. I can use the binomial series to, I can truncate the series, right? Because how's the series? What was the deal? We learned this. It was what, 1 minus 1/2 u plus minus 1/2 times minus 3/2 u squared, right? Right? Where my u is what? Minus v squared over c squared, right? So putting that in, we've got 1 minus 1/2 v squared over c squared. Well, actually, minus a minus gives me plus, right? So plus v squared over c squared plus 3/4 v to the 4th over c to the 4th plus dot, 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 dot. So for very small speeds, really, the first two terms in this expansion are dominant, right? So a very good approximation of E, the relativistic energy, m sub 0 c squared times what? 1 plus 1/2 v squared over c squared plus dot, 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 dot. And so what do you got? You have m0 c squared. The c squareds cancel. We get 1/2 m sub 0 v squared plus dot, 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 dot. So in this case, it's very interesting what's going on. If you've had Physics 231, most of you are currently experiencing Physics 231, right? How's your experience so far? It's good? Okay. Yeah, don't tell me. If it's bad, don't tell me. But one of the things, of course, that you have by now discovered is that kinetic energy makes everything that you did in the first 2 weeks of the course way easier, right? So there you go. This is the classical kinetic energy, right? And then this right here is what's called the rest energy. And the reason it's called the rest energy is, well, if the speed was 0, right, if v was 0, everything beyond that term is 0, right? And you're just left with m0c squared. So this was pretty shocking, I think, in the early 20th century when we found this. We found out that there's this incredible energy inside matter that's just sitting there, right? It's way, way bigger than the kinetic energy, the scale, right? Just waiting to be used. Or ignored from a generation of ignorant environmentalists. But anyway. Yeah. Sorry. I'll try to stay apolitical. Another example. Another example I should mention is Newtonian gravity. Do you guys know how? Well, many of you are in Physics 231, right? So if I put the Earth like here, right? And I put a satellite, whatever, out here. What's the force of gravity on this? Yep. GMM over the radius squared. Well, let's say that this is the radius here, r. What do you call the distance above the Earth? Well, we could call it x for the sake of discussion. Usually we call x equal to h for altitude or for height, right? But you're right, it's r plus, it's the distance between the center of mass of Earth and the center of mass of satellite, so it's really r plus x quantity squared. This is Newton's law of gravitation, right? The inverse square law. But what do you guys do from like week 1 in Physics 231? You say F equals to what? F equals to mg, right? How can F equal to mg and F equal to gmm over r plus x squared at the same time? What's up with that? Do you guys know the answer? Because of the constants calculated? But it seems like this g can't be a constant. It has to be like this g, the m, and over the rx. I mean, how's that work? Well, here's how it works. If we think about this as being, say, f of x, right? Then we can approximate f of x. Well, we can replace f of x with its Taylor series centered at 0, right? What's the Taylor series centered at 0 look like for this? It's f of 0 plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared, right? So what does the Taylor series here for Newton's universal law of gravitation in this context look like? What's f of 0? G little m, big M, divided by the big radius squared, right? And what's the derivative of this? If I differentiate this, what do I get? R cubed, right? I have to differentiate and evaluate at 0. Can you see that in your mind's eye? If I differentiate the minus second power, it gives me minus 2 upstairs. It increases the second power in the denominator to a third power because I'm differentiating. I plug in 0, I get this, right? Times x. So it turns out that if you calculate g big M divided by the radius squared, it is very close to what we call g. Actually, let me not be vague about this. Let me show you the details. See, because we have the technology in here, mathematically speaking, to, come on, you can do it. Oh, the computer's so lazy it keeps turning itself off. Here's that proof I was just talking about at the start of class. Let me go back to my notes. So I plugged in the numbers. If you plug in GM, like I said here, if you put the radius of the Earth is about 6.3675 times 10 to the 6 meters, typically. The mass of the Earth is 5.972 times 10 to the 24th kilograms. If you plug that in and you calculate, oh, there is a typo right here. This little m does not belong there, right? That little m is a typo. It's supposed to just be big G, big M over r squared, about 9.83 meters per second squared. So what this means, guys, is that the thing you've been doing, you didn't realize it, but from the very start of the semester in physics, you're using a Taylor series. F equals to mg is a Taylor series-based approximation in some sense. Like, it's just taking the 0th term in the Taylor series for Newton's law of gravity. How wrong is that? In other words, precisely what's the error in that? Well, we have a theorem, Lagrange's form of the remainder, that says the difference between the actual function and the power series which approximates it, if you truncate the power series at a Taylor series, it's given by the size of the next term depending on like how x varies, right? So specifically, the error in f of h is really given by this 2gmm h over r cubed term. So the error in saying f equals to mg, the absolute value of the error is something like 2gmm over r cubed h, where the error, of course, depends on the mass, the mass of the satellite. The bigger the mass of the satellite, the bigger the error. And anyway, so something like 3.1 times 10 to the minus 6 times the mass times the altitude is the error in mg. So if you're close to the surface of the Earth, that's stupidly small, and we can get away with f equals to mg, and it really doesn't. It's not an abuse, right? Yep.
Is R, G, and M, are those constants, or are those just like given to us?
Those are constants. The big M, the big R, these are given constants. It's the radius of the Earth, okay, and the mass of the Earth. These, of course, I mean, this is idealization, right? So specifically, what the value of the specific value of gravity at the surface of the Earth depends on your actual distance from the center of the Earth, which might not be the mean orbital radius. I mean, the Earth, after all, is an oblate spheroid. It's not actually a sphere. It's kind of squished out at the center, right? And so this is sort of a rough calculation, but it gives you a sense of the kind of errors that are involved. And so just to be specific, I went ahead and calculated some things, like if your altitude, you could look at the ratio of f over m. You could look at the ratio of e over m, the error over m. And if you do that for 1,000 meters, you're only about 0.0031 meters per second squared off, right? That is smaller than the, if you look at the force of gravity at the center of the Earth versus the poles, there's like what, about like a 0.2, is that right? About 0.2 meters per second squared difference, just based on like centripetal corrections at the equator. versus the poles. At 10,000 meters, 0.03 meters per, so you got to get up to about 10,000 meters before you're kind of in the same scale as the correction versus, you know, of where you are on the Earth versus poles versus center of the Earth where you're spinning, you know, the Earth spinning around its poles trying to throw you off, right? That essentially makes gravity smaller, right? If you could somehow speed the Earth up a little bit more, if you could shorten a day enough, you could make people weightless at the equator. They'd start flying off, right? But it wouldn't just be the people; it'd be everything. You wouldn't want to be there, you know. You really don't want to do that. To see why, if you could take a CD and like spin it up to about 10,000 RPMs and see what happens. Actually, you don't need to do it. There's these guys on the internet who've done it for you. You can go watch those videos. Anyway, at 100,000 meters, the error is about 0.31 meters per second squared. So you got to get up to an altitude of like 100,000 meters before you're even to 0.3 meters per second squared correction to F equals to mg. It's a very good approximation for the Earth close to the surface. Anyway, these are the kind of things we can make precise if we use Lagrange's form for the remainder. In fact, it's not even that. If you look at this, we don't even need Lagrange's form for the remainder, right? Altitude's positive. What kind of series do you have here? Plus, minus, plus, minus. I'm pretty sure it goes plus, minus, plus, minus, plus, minus. It's an alternating series. So this term has an error which is at most the size of that term. You don't even need the full-blown Lagrange's form of the remainder stuff. You can fall back on the alternating series estimation theorem to get a sense of how big the error is. And this is like sort of generic, somewhat careless comment on my part, but even when the series is not alternating, it's often the case that the alternating series estimation theorem is still a good rule of thumb. The next term you're not using probably is something along the size of the error, ballparkish. That's not a precise mathematical statement I'm making. It's just a pragmatic statement. Anyway, so that's pretty much all I got to say. There's one other throwaway. I mean, I just want to mention something else here. On page 102 in the handout, there is something called Abel's theorem or Abel's theorem. You may recall that I calculated the natural log of 2 by calculating the geometric series for the natural log of 1 plus x, and then I plugged in the endpoint, but technically speaking, the endpoint is where we're not sure it makes sense. I said we're not sure it makes sense. Abel's theorem says it makes sense. This says that if you're finding a Taylor series approximation to a function, and that function's continuous and it converges at the endpoint, then this says that we can extend to the endpoint. Even though I can't do power series calculations at the endpoint, I do a power series calculation and then take the limit as I approach the endpoint, it's still legit. This is Abel's theorem. And then finally, last comment, and then I will not prove this, don't worry. Oh, come on. What the what? Where'd you go? This is at the very tail end of his chapter 12. He proves that the derivative, the term-by-term derivative of a power series is actually the derivative of the power series. The proof is given here. It's somewhat delicate. You know, he's looking at the difference quotient of f of x versus g of x, where g of x is the term-by-term power, term-by-term derivative of the series, and he shows that this has to be small. But it's a fussy argument, which I covered one semester. Anyway, it's there. If you're a math major, I would encourage you to read it. Finally, and with this I will actually turn the floor over to you guys, I should mention I've done some research in the past couple years with a student here, and we wrote this paper, Theory of Series in the A Calculus and the N Pythagorean Theorem. Daniel's now a graduate student at Indiana University. But in this paper, what we did was we studied series and sequences, not over just the real numbers, but over like what's called an algebra. So complex numbers are the first example of this. Right? Complex numbers are an algebra. There's something called hyperbolic numbers, which are kind of the next more interesting thing. They look like this. A plus bj, a, b real numbers, j squared equals to 1. So these are so-called hyperbolic numbers. They're like complex numbers in the sense that they're two-dimensional, but they're really different in terms of the analysis. And what we found was that pretty much everything we've done in this course still makes sense over an arbitrary algebra. But there are some surprises. I'll show you one of them. First of all, the proofs got more complicated, which was annoying. Like, here's the limit, the proof of the sum of the limits, the proof of a number times the limit, the proof of the product of two sequences being, like the proof of the product of two sequences being the product of the limits. That star is the algebra multiplication. It looks like this. Ugh, right? Ugh. Yuck. But anyway, moving on here. The thing that was, everything was kind of like, the proofs are more ugly for sequences, but it's kind of the same. Everything was fine and dandy. We got the series, and we still got root test. We still got ratio test. Everything's going along just fine. Yay. Great. Fine and dandy. And then we got the power series. And by the way, this is a theorem for series. You can prove that if you have two absolutely convergent series, their product series is defined. And here's the, well, anyway. Power series, though. Let me show you an example. So this was the example that was vexing. If we have the series sum n equals to 0 to infinity of 1 plus j times z to the n, all right? I apply the root test, which you guys know, right? It still makes sense here, actually. And the root test works out to show me that this series should converge for this whenever it's like within distance 1 over ma alpha, which works out to 1 over the square root of 2 here, given whatever ma and alpha is, okay? And that's fine. But then what I learned was that, in fact, the series converges outside of where the root test says it could converge. In fact, this series converged on the line y equals x. No, rather y equals minus x. It converged on the line y equals minus x for arbitrary a. So what this says is that there's points of convergence sometimes outside where the root test says it should converge. So like the ratio and root test ceased speaking to where the series diverges. They just tell me where it converges, and like there's all kinds of weird stuff that happens for the theory of power series. Domains are not just disks, and it's uglier. But anyway, the other thing that I should mention in here, there were some surprising things, is my point. What you might find amusing here, this theorem 5.19 is the analog of what I just showed you at the end of chapter 12 for arbitrary series. This took me a long time to really get. It was like a week of my summer. That's the hardest thing in this paper. What you might be amused by, though, is at the end of this paper, we define, Daniel and I, we define the exponential, sine, cosine, hyperbolic cosine, all in terms of power series over an algebra. And then we work out your favorite properties, like what's the exponential of z times the exponential of w? It's the exponential of z plus w, right? And also the adding angles formulas for sine and cosine, all derived from power series. You can use power series to define things and actually work things out. I wasn't making an idle statement the other day when I said this. We've actually worked it out. It's all in this paper. So like here, definition for Cauchy's inch, and you know, you can, of course, work out Cauchy squared minus inch squared is 1. More than that, though, you know, you can give arguments that Cauchy of z plus w is that, and sinh of z plus w is that, completely using laws of exponents, and which rest on power series, and even sine and cosine. We have power series based arguments to prove that adding angles formulas for sine and cosine are true. Anyway, I shut up. I've said too much already, but I want to share that with you. My personal research has been very much based on calculus the past few years when I have done something with students. It's actually been a sort of, part of it's a straightforward outgrowth of calculus 2. Now, I don't think people are ready to do this after calculus 2. Like the student who did this paper with me, he'd already had, about 6 courses past where you guys are. But it really is just the straightforward abstraction of what you're doing. I shut up. This is not on the test. Do you guys have questions about your homework? If I can find it. Yeah. 95, please. So I will, of course, I will take more questions about homework as we go on this week. But that's, as far as I can remember, that's pretty much everything I have to say about power series in here. Oh, I think I've assigned you a homework problem where you use power series to derive the solution to a differential equation, but that's actually when I'm probably going to turn the page tomorrow and start talking about differential equations. Get us ahead a little bit. All right. Okay, so 95. Find the first 3 non-trivial terms in the power series centered at x equal to 0 for f of x, 1 plus x squared, sine of x. All right, so what's that? Oh, centered at x equal to 1. So what do you guys think? There are 2 paths we can go down here. Yeah. So here's the 2. One path would be f of x is equal to f of 1 plus f prime of 1 times x minus 1 plus 1/2 f prime prime of 1 times x minus 1 squared, right? That's one path we could go would be just straight calculate the first 3 terms in Taylor's series. That's not too bad here. I mean, that's a legit path for the solution here, I think. The other way to do would be to replace x with x minus 1 plus 1 and use substitution. Those are the 2 things I would think about doing here. Yeah.
How do you know that it's analytic, that it can be defined by the Taylor series?
Oh, because the product of analytic functions is analytic.
How do you know that?
Let me just say it this way. Everything in here is analytic, except for that one example I gave, which is not. It's really hard to break analyticity. Like, it's not easy to come up with. Yeah. So, what does that look like? I mean, so what do you think, Hannah? Which path do you want me to? I'll do a little bit more on the substitution. I won't finish it, but I'll get it started here. So f of x would be what? 1 plus, and x minus 1 plus 1 squared, right? Times the sine of x minus 1 plus 1, right? Now that is what? You got yourself a 2 plus twice x minus 1 plus x minus 1 squared, right? There's no need for a plus dot dot dot. That's just literally what x squared expands to at x minus 1. Excuse me, 1 plus x squared, right? Now the other one, how do I deal with this? See, that's going to give me a cosine of 1 times the sine of x minus 1 plus the sine of 1 times the cosine of x minus 1. So honestly, for this one, I tend to favor Taylor's theorem directly for this one because it's just enough trouble here to make it maybe not worth my while. But then, by request, let's see here, cosine of 1. This is what? X minus 1. Minus 1/6 x minus 1 cubed. And then plus the sine of 1, 1 minus 1/2 x minus 1 squared. And that, at this point, we have enough that we can start, like collecting terms. What's the constant term? When I have something like this, I don't just multiply it out without thinking. It's tempting, because you guys like to multiply things, right? Because it's like a happy place. You know what you're doing, right? But should you do it? And you got to keep your eyes on the prize, right? I mean, what's the prize? The prize is the power series, order by order, from constants to quadratics, constants to linears to. So constant here, there's a 2 times the sine of 1 times a 1. So the 0th term here is 2 sine of 1. Yeah. Which, by the way, f of 1 is what? 1 plus 1 squared times the sine of 1, also known as 2 sine of 1. It's pretty obvious that that's easier to get by Taylor's theorem directly here. You're like, I thought you said it was easier not to use Taylor's theorem. I didn't say that. I said often it's easier to not use Taylor's theorem directly. There are two different paths you can go down. In the end, it's still the same road that we're on, Someone said once upon a time. How about linear terms? The linear terms, this times that gives me quadratic. That's no good, right? But this, that's quartic. That's worse. So it looks like that's the only way I can get linear term, right? So plus 2 sine of 1 times x minus 1. That's the only way I can get a linear term, right? And by the way, what's f prime of x equal to? 2x sine x plus 1 plus x squared cosine x, right? What happens when I look at f prime of 1? What do I get? 2 sine of 1 plus 2 cosine 2. Well, I got one of those terms. Looks like I missed something. How did I miss it? Yeah. Uh-huh. Ah, yes, I missed the 2 times the other. I missed. And you see how easy it is to make a mistake in this multiplication way of doing things, right? That times that gives me plus 2 cosine of 1. But of course, it would be harder. But you might still miss that with differentiation if you don't remember the product rule. On occasion, I see you guys forget the product rule. Not knowing the product rule at the end of Calculus 2, it's a good way to retake Calculus 2. I don't want that to happen, but I do believe in recycling. So anyway, there's the first 2 terms. I think the homework asks for more. So I haven't done your homework problem yet, but I started it. What's that? Yeah, you guys can go if you need to, but I'll look at 97 here. Oh, let me just be really fast. 97, the way to do that, x to the 7th, what was it, sine of? So basically, to integrate this, you take the sine, make a substitution, convert it to a power series, clean it up, next clean it up, and then do integration term by term. Did I copy down wrong? 7x cubed. Oh, my bad. Sorry. And so, I think. Listen, I will start class with another like half hour of this tomorrow, okay? Sound good? All right, yep. We do not have class on Wednesday. Wednesday is a classless day. What's that? Are they going to send an email about that? Well, so you guys have not been sent an email saying, hey, you don't have class Wednesday? You have been? You may or may not have some sort of like a department-based obligation, Yeah, you probably would have gotten an email about it, so. I guess you can go sledding or something, I don't know. Maybe there'll be snow. I don't know, just talking. Happy Convo to you all. What's that? This is just a start, halfway point. Yeah, now you got to integrate term by term. The